Could black holes hold the answer to a quantum theory of gravity? A more profound framework for understanding how reality, space, and time truly function. Black holes are fascinating because they contain a region called the event horizon, where we believe our understanding of physics is complete. We grasp what's taking place there, yet our two foundational theories of nature, quantum theory and general relativity, are fundamentally at odds. The effort to combine these two great cornerstones of 20th and 21st century physics into what is often called a quantum theory of gravity is, in a way, the ultimate goal for theoretical physicists. Consequently, black holes compel us to seek a more profound comprehension of what space and time are. For this reason, I believe it's accurate to say that black holes are the keys to unlocking the universe's secrets. I'm Brian Cox, a professor of particle physics at the University of Manchester and the Royal Society Professor for Public Engagement in Science. Among other things, I am the author of the book, Black Holes: The Key to Understanding the Universe. The concept of black holes has existed for a very long time, actually since the 1780s and 1790s. Two physicists, mathematicians, or natural philosophers, whatever you prefer to call them, came up with the same idea independently around that time. One was a clergyman named Mitchell, and the other was the great French mathematician, Laplace. Both were contemplating the concept of escape velocity. Escape velocity is the speed required to completely break free from the gravitational pull of an object like a planet or a star. For Earth, for example, the escape velocity from its surface is approximately 8 miles per second. If you increase the size and mass of an object, say a star like the Sun, the escape velocity rises to somewhere around 400 miles per second. Escape velocity increases as the gravitational pull at the surface grows stronger. Mitchell and Laplace had what I think is a truly beautiful idea. They wondered if it was possible to go even bigger. They imagined more and more massive stars, colossal stars where the gravitational force at the surface was so immense that the escape velocity would surpass the speed of light. If that were the case, you wouldn't be able to see them. To grasp why black holes pose so many conceptual challenges, it might be helpful to briefly describe what one looks like. So, what do you see from the outside of a black hole? Well, it's surrounded by an event horizon. This horizon essentially marks the boundary between the universe outside and the black hole's interior. If you cross this boundary into the sphere's interior, you cannot escape the black hole's gravitational pull, even if you could travel at the speed of light. However, another way of describing the event horizon, which has caused confusion throughout the history of black hole research, is the idea that, when viewed from the outside, the event horizon is a point in space where time stops. This is a direct consequence of Einstein's theory of relativity. From an external viewpoint, there remains a central unsolved problem. What is at the center of a black hole? You might visualize it as an infinitely dense point where the massive star has collapsed. We call this a singularity. It's not truly accurate to speak of the center of a black hole, though. Even in pure general relativity, if you look at a diagram of a black hole, known as a Penrose diagram, after Roger Penrose, you see that space and time are so warped that they essentially switch roles. The singularity isn't really a location in space at all. It's a moment in time, and it's actually the end of time. The nature of this thing was not, and is still not, understood. For many years, people thought, well, the singularity is a problem. We have no way to access it, or the conceptual tools to explore it. It might remain a mystery for another century. It's unclear what we can do. The major breakthrough in black hole research came with the realization that conceptual problems exist not just in the extreme region of the singularity, but also at the horizon. Stephen Hawking demonstrated in a couple of groundbreaking papers that if you apply quantum theory near the event horizon of a black hole, you find that they emit light. They have a temperature and produce particles. This object, which Einstein's theory described as pure geometry, just warped space and time, actually radiates particles. This is known as Hawking radiation. In his 1974 paper, Stephen offered a less formal but helpful way to visualize what's happening. The idea is to zoom in on the area near the event horizon of a black hole. You can picture it as a constant stream of particles appearing and disappearing, known as entangled particles. One particle of a pair is inside the event horizon, and the other is outside. It's possible for the one on the outside to escape into the universe instead of rejoining its partner. As it leaves, it removes energy from the black hole, causing it to shrink, which means it will eventually vanish. This has profound consequences. Black holes are not permanent prisons, they have a finite lifespan. Eventually, whatever fell into them is returned to the universe. The core question that immediately arose from these calculations was what happened to all the matter that fell inside. Based on my description and Einstein's theory, that matter seemingly goes to the singularity, whatever that is, the end of time, a region of space-time so twisted and convoluted that we can't describe it at all. But then one day, the entire thing is gone. All that remains in the distant future is Hawking radiation, the particles generated near the event horizon. The question is, if you could collect all that radiation throughout the black hole's entire life, would it be theoretically possible for the information about everything that fell into it to be encoded within that radiation in the far future? Is this true or not? You might wonder why this is such a crucial question. It's because as far as we know, information is conserved in the universe. Every law of nature we have says that information cannot be destroyed. For example, if I take a book and burn it, or destroy it in any way, fundamental physics says that if you could collect every last piece of the incinerated object, every quantum of radiation, every photon, every particle, everything, it would, in theory, be possible to reconstruct the original book. The problem was that when you combine black holes, quantum mechanics, and general relativity, you get this apparent prediction that black holes erase information from the universe. This became known as the black hole information paradox. If we jump ahead to the present day, with new papers still being published, the general consensus is that black holes do not erase information from the universe. We now believe you could collect all the Hawking radiation and, in principle, feed it into a quantum computer to reconstruct the information about everything that fell in. The implications of this, the mechanism by which this happens, are, in my opinion, incredibly exciting because it seems to offer us a glimpse of a more profound theory of gravity. To put it simply, it appears that space and time are not fundamental. One perspective, and I want to stress that other viewpoints exist at the cutting edge of research, is a field known as emergent spacetime. The idea is that space and time themselves arise from something else. From what? From quantum entanglement, from some kind of smaller components or pieces. We don't know what these things are or their nature, but it does seem that there is a deeper, underlying theory from which space and time originate. This is what we call the quantum theory of gravity. My view is that if we want to discuss the universe's origin, and even ask questions like whether the universe had a beginning in time, which we don't have the answer to, then it seems essential that we first understand what space and time are. We must do this before we can even begin to answer such questions. And it turns out that black holes are the objects we can actually see and observe in nature that force us to take this path. They compel us to ask precise, defined questions about the very nature of space and time. Einstein once said that if you study nature very carefully, pulling at the intellectual threads, and continue to delve into what nature seems to be telling us, then with luck and persistence, you can catch a glimpse of something deeply hidden. That's a beautiful thought, isn't it? A glimpse of something deeply hidden. The profound underlying structure of nature itself, the deep underlying structure of reality. And I find that very beautiful. I think it's fair to say that no one truly knows where this is all heading, but it hints at something deeply hidden. Get smarter, faster, with videos from the world's biggest thinkers. Want to learn more? Become a Big Think member and join our members-only community. Get early access to videos and unlock full interviews.